Okay, we're looking at part 2 of Unit 3C and dealing with uncertainty. So we've just talked about significant digits. Now we want to state the number of significant digits in numbers 20 and 22 and the implied precision of the following numbers. So the first number, 350,000 years. Okay, so we have 3 and 5. Those are definitely significant digits because they are non-zero digits. But then every zero after that is not significant, and that will follow kind of this last point right here, that those zeros are not significant unless they were to throw a little decimal on the end there, which they did not. I'm sorry, make this big full screen. So this has 2 significant digits, and the precision of this thing is as precise out to the 10,000s. Because it's 350,000, so we have the 100,000 place and then the 10,000 place, and that's where the last significant digit ends, so it is precise up to the 10,000th place. Okay, number 22, we have 0.004502, so all 4 of these are going to be significant. Again, this 0 is significant because it is between, so that's this rule right here, it's between 2 non-zero digits, so it is significant. But then the first couple of zeros right here, those are not significant because they are to the left of the non-zero digits between the decimal points. So we looked at these examples up here above. So this one is going to have 4 significant digits, 4, 5, 0, and 2. And it is accurate. Now if you count it out, it goes the tens, hundreds, 1,000, 10,000, 100,000, and then millionth. So this is all the way out to the millionth that it is accurate. And probably should say millionth of a meter, and the first one would be 10,000 years because we have those units there. Okay, so that's how a couple examples how you would determine the number of significant digits. Now sometimes we can be asked to divide or do an operation mathematically and then round it to the number of significant digits that we're asked for, which is, in this case, they're asking for 2. So if I take 988 and I divide it by 10.3, that is going to equal, when I throw it in my calculator, I'm going to get 95.92233, and it just keeps going. But to 2 significant digits, that means I'm going to, once I hit 2 significant digits, I got to cut this thing off. So the first significant digit is going to be 9. The next is going to be the 5, and I have to cut it off there. So I need to make sure I properly round, so that would round up to 96. And there are my 2 significant digits, so it's significant to the ones place. So you always kind of start left to right when it says, give me this many significant digits. I grab the 9 first, and then I grab the 5, and that's where it ends, but I have to make sure I round the 5 properly. Okay, now when we're making some measurements, there are errors that can come in measurements. So as we look at uncertainty again in numbers, we're shifting gears here. Now we're going to talk about some different types of errors that are out there. So there are what are called random errors. Okay, and random errors occur because of random or inherently unpredictable events in the measurement process. Okay, and we'll look at that example number 38 here in a minute. Then next is what are called systematic errors, and these occur when there's a problem in your actual measurement system. And it affects every measurement in the same way, such as making them all too low or all too high by the same amount. So, I mean, if you're looking at a weight scale or something like that, and the scale is wrong, okay, that's going to be a systematic error because the scale is measuring it wrong for every person, whereas a random error might be if you're on a scale and one person comes in and they've just got this enormous set of keys that weigh a pound. That person is going to be off, but that doesn't affect everybody. So that's the difference between a random error and a systematic error. Let's look at number 38. Describe possible sources of random and systematic errors for the following measurements. The number of votes cast for 2 candidates in a U.S. Senate race. Okay, so if we look at some random errors that that could occur here, a lot of the random errors are going to come in, the actual counting of the ballots. There could be a random error where someone is counting by hand. They miss one here or there. It's just a human error, or by machine. The machine could misread something, or someone didn't fill in the one dot properly, so the machine doesn't read it properly. So those are what we call random errors. They happen by chance, and they're very unpredictable. Okay, then there are possibilities for systematic errors. Okay, and some systematic errors that can affect the entire measurement system are if someone loses ballots. That affects the whole measurement system if you lose ballots. So say someone misplaces 10,000 ballots, that's going to have a dramatic effect systematically wide. And so that would be a systematic error. Another systematic error that you can run into is double counting. Okay, so some ballots, they may have got counted by one person and then somehow got back in the stack and got counted again, or you may run the machine once and then run it again on that. And that's a systematic error that, again, it affects all the measurements in the same way. And if it's systematic like that and you've determined that, then you can make adjustments accordingly. But those are things that you can actually identify, whereas the randomness, it's very hard to identify those. They just happen kind of unpredictably. Okay, next we're going to talk about an idea called absolute and relative error. So the absolute error just describes how far a measurement or a claimed value lies from the true value. So the way we determine that is the absolute error is just your measured value minus your true value. So if in truth you weigh 165 pounds, but the scale shows 163, then your absolute error, you're going to be off by 2 pounds there. And so that would be -2, you're 2 pounds below. So that would be the absolute error. Relative error compares the size of the absolute error to the true value and is often expressed as a percent. So you take this absolute error, which is measured value minus true value, divided by the true value and then times it by 100 to get a percentage. Okay, so if I weigh 163 or 165 and the scale shows 163, so I'm off by a couple of pounds, I'm going to have 1.5-ish relative error there where I'm off. So, and it would be negative because we're measuring low. Okay. So the next couple of things we're looking at are accuracy and precision. And let me check my time here. We're doing okay. So two ideas that are actually key when we're reporting a value is accuracy and precision. Now, although these, you may often use these interchangeably, they're definitely not the same thing. So the goal of any measurement is to obtain a value that is as close as possible to the true value. And accuracy describes how close the value lies to the true value. However, precision describes the amount of detail in the measurement. And so, for example, suppose the census says that the population is 72,453, but the true population is 96,000. Okay, the census value of 72,453 appears to be quite precise because it seems like it's telling you an exact count. However, it's not accurate. It's not very accurate because it is nearly 25% smaller. I mean, it's way off. 72,453 compared to 96,000. It's accurately speaking, it's quite a ways off, but the number that we're originally given, the 72,453, is very precise. And that's where we talk about uncertainty, where numbers can be used in a way to deceive. Is, that looks like they are right on the money, where in reality they were not very accurate. And so accuracy is usually defined by the relative error rather than the absolute error. And for example, if a company projects sales to be 7.3 billion and the true sales turn out to be 7.32 billion, we can say it's quite accurate because the relative error is less than 1%, even though the absolute error is $0.02 billion, which is $20 million. So if someone says you're off by 20 million, you're like, whoa, you're way off. That's terrible. But in reality, the accuracy is less than 1%. And so if we use the relative error, that will help us compare things much more easily than if we use the absolute error when we're looking at accuracy. So because $20 million in one context could be huge, but in this context of billions of dollars, it's actually not that big. It's just a fraction of a percent. Okay, so there are definitions of accuracy and precision. So now we're going to, in the next video, we're going to take a look at a couple of examples and then end off with how we find significant digits when we're combining measurements and adding and multiplying.